Yeah, very well. So it's 2 o'clock.
Right.
So UTC plus 0, 2 o'clock. So welcome everybody back to our today's afternoon lectures. So I'm very happy to welcome John Gough today, who will speak about Trotter-Kato theorems for quantum Markov semigroups. Please, stage is yours.
Okay, so first of all, can you see the screen being shared?
Yes.
So you should see this lime green announcement with the title. Okay, well, I'm very grateful for the organizers for inviting me here and really appreciate the great work they've put into this conference. It's turned out very nice altogether. There have been quite a few talks so far involving quantum stochastic processes, quantum Markov semigroups. I'm going to talk about a particular element of this, and what I taught for the purposes of this particular conference, with its emphasis on one parameter semigroups, I'd focus on a collection of results which I've had some contribution to, but largely just to discuss the general approach overall and how it applies certainly to our theory of quantum open systems, but possibly well beyond that. So I'll start off with a little bit of an introduction to the general ideas behind this, just for people who may or may not be familiar with what's gone on in quantum stochastic calculus, what the central ideas are. The focus I'm going to have here is on Trotter-Kato theorems. And just to make clear that there have been a number of people here already talking about Chernoff theorems. This is not Trotter-Kato in the sense of the Trotter-Kato type result for a product formula. It's two theorems proved independently by Trotter and Kato. So it's a separate result from that, largely connecting the uniform convergence of semigroups of contractions to convergence of the generators, a type of graph convergence. So elements of this can be found in, for instance, the book of Nagel and Engels, which we've heard mentioned a couple of times, but I'm going to be looking at the specifics related to quantum stochastic evolutions and dynamics in general. Okay, so I'll start off with some simple things and try and get progressively more complex as we go along. So let's start off with the beginning. So we're interested in semigroups in this particular workshop. So we'll start off with quantum mechanics, in particular closed quantum evolutions. And there are two types of semigroups which arise, and they're really associated with the Schrödinger picture and the Heisenberg picture. So we'll first of all assume our system has a well-defined Hilbert space H. And of course, in quantum mechanics, the physical observables correspond to the self-adjoint operators on the Hilbert space. In the Schrödinger picture, you can consider the vectors in the Hilbert space as evolving in time, and they evolve according to a unitary. So you've got a family of unitaries. It'll be strongly continuous. It's a group under the usual product of operators. So we should, from Stone's theorem, have a generator. And of course, the generator is related to the Hamiltonian of the system. However, we can also look at the Heisenberg picture where the states are fixed, and instead we consider the observables, or more generally operators, as evolving. So in this case, the evolution is given by effectively an automorphism, and it'll be a family of automorphisms phi t, which corresponds to unitary conjugation of an observable with the same unitary u occurring in the Schrodinger picture. So u dagger t x u t. So again, this is strongly continuous. It forms a group. It's a group of automorphisms. Phi t composed with phi s will be phi t plus s. So in that sense, it's a group under composition. And of course, the generator here will take the following form of just a commutator with the Hamiltonian. Again, the same Hamiltonian that's acting as generator for the Schrodinger picture dynamics. Okay, I haven't discussed domains here, but obviously the generators are to be understood on the respective domains. Okay, so that's closed quantum evolutions, but we've been talking quite a bit about open quantum evolutions. And to give an example of this, what we could do is just remove the Hamiltonian altogether and just consider what would happen if we allowed our system to evolve according to the following unitary. So it's a unitary family parameterized by time. We have a self-adjoint operator or, and we have e to the minus or, and instead of time, we take something like a Wiener process. Okay. So the Wiener process, again, I'm assuming some familiarity with stochastic calculus here. The increments of the Wiener process aren't actually negligible, and you have this quite nice formula that the increments of the Wiener process squared can be considered as dt. So you get this very nice second order calculus. It's a second order correction to things like Taylor's theorem and so on. Of course, the Wiener process is described on a probability space. We can take this to be sample space of paths. So this is the canonical construction by Wiener. So really the process then can be considered as a function of the outcome, which is the particular Wiener path that's followed. These are almost everywhere continuous. And at the end of the day, we can consider the evolution under a particular realization of this, and then average out overall possible sample paths we could have had. So this gives us an average evolution. It turns out that this has a semi-group structure. It turns out to be strongly continuous as well. Because we're averaging unitaries, it's going to be a contraction semi-group. And the generator, let's keep it simple. Let's take all bounded. It's just going to be a double commutator with respect to OR. So this double commutator signifies that it's not a derivation anymore. It's not just a single commutator. This is something genuinely dissipative. Okay, a second example.
Excuse me?
Yeah?
May I ask a brief question? You mentioned strong continuity in the space of bounded operators, but I think we don't have the zero property there, right?
We don't have the what?
It's not strongly continuous on the space of bounded linear operators. The action on B of H. Mentioned on the previous slide.
Yeah.
Pointwise weak star.
Yeah.
Thank you.
Yeah, probably right. Okay. An alternative procedure is to use a possum process. So we fix a unitary S, and the possum process is a counting process. So it takes the value 0, 1, 2, 3. It's increasing, but increases at random times. Again, it has its own calculus, so you can develop an Ito calculus around this. The n squared is equal to the n. So the idea is that at these possum times, we apply a unitary kick S to our system. And again, we're going to consider the unitary conjugation with U of t and average it over the possum process here. What you find again is that you get a generator, and the generator will take this form here. Okay, so this is the idea of having a random evolution, which you then average over. And because of the particular structure here, we're ending up with semigroups. Right. So within these lectures, we've been talking a little bit about complete positivity. Complete positivity, just to give a definition of it, if we do consider a map, say in general from a C-star algebra B to itself, we'd naturally require it to be positive if we're talking about something which would be a morphism for observables. This would imply, again, positivity of the probabilities. However, we can ask for a further requirement. We can take a map and basically tensor it with the identity on, say, an n-level system. So its algebra will be the algebra of n by n matrices. So this may at first sight seem rather trivial as an evolution, because all it's really doing is evolving the observables of B, and it's apparently trivial on the n-level system. However, we don't necessarily have positivity. Positivity of phi alone doesn't necessarily imply positivity of this extension. So one way of thinking of this extension is as follows. We consider the algebra B tensor Mn as the n by n matrices whose entries are just operators in B. So the application of this extension phi tensor, the identity n, is really just to apply phi to each of the matrix elements. So we say phi is n positive if this is going to be positive for that particular value of n. So that turns out to be a genuine condition, and it's completely positive if it's positive for all n. So this is by now standards in quantum information theory, for instance. But really, this goes back to Krauss and has played quite an important role in quantum probability considerations for several decades now. Okay, so what we would like to do is to consider the semigroups of completely positive maps. And one of the questions you can ask is whether or not the whole family is going to have a unitary dilation. So that is, can we find a second space which is going to act basically as the environment, which we're going to couple our system to, and a state on this environment, so that we can view the dynamics as follows. We have any observable of our system can be embedded in the system tensor, its environment. We apply a unitary conjugation, and we've got, say, some family of unitaries on A tensor B. And it's effectively the reduction, the averaging out of this object with the state sigma we impose on the environment will reduce us down to the CP semigroup. So it's worth mentioning some results here. First of all, if we insist that A is commutative, right? So we can say this is an essentially classical environment. The problem of finding the most general class was solved in 1987 by Masson and Krummerer. And they showed effectively that what we've already looked at, the deterministic part, so Hamiltonian, the Wiener cases, and the Poisson case, which we've looked at, it's a combination of these that give you the most general class of generator of everything's classical. Okay, so that tells you that if we want the environment to be classical, and if we want dilations to be just stochastic dilations using commutative processes, we're restricted in the class of generator we can actually achieve. So this brings us to a more general situation presented by Hudson and Partha-Sarati. So we've had a number of talks today on this. Effectively, we take our environment to be the algebra of observables over Fock space, and we'll take the Fock space to be the L2 space over R plus, and we can think of the variable here as being time, so it's positive times. I'll just recall some of the ideas which you've seen in several talks now. We have the exponential vectors. So these are the vectors on the Fock space defined as follows. So for a particular test vector F, one particle vector, we have this general sum where at each level of the Fock space, the nth level, we have just the test vector F tensored with itself n times with a weighting of 1 over root n factorial. And for n equals 0, we've got the vacuum state. Okay, so the inner product of two exponential vectors is just the exponential of the inner product of the two test functions, the total set in the Fock space. And so, for instance, the annihilation process, which we've heard mentioned a couple of times recently, can be defined quite simply as follows on this particular domain. Okay, so again, I'll just repeat the quantum Ito table. So you can develop an Ito-type theory of integration on Fock space. We have the creation, the annihilation, and the lambda process, which is sometimes referred to as the gauge process. This is the Ito table which accompanies it. So we've seen this in several guises. You can also describe this at the level of white noise, which Henry Norden did formally in his talk a day or two ago. And if you're specifically trying to construct dynamics where you have a system space, usually referred to as the initial space, tensored with the Fock space, on this base, you try and construct a unitary dynamics, which will be the solution of the following quantum stochastic differential equation. So there's a lot of machinery here, which I'm not going to go into. It turns out that on the Fock space, we have a continuous tensor product decomposition. So at each time, we can divide it into a past and future space. The increments here are all understood as living on the future component, which is the operator way of doing things, operator theoretic way of looking at the Ito calculus. The process UT itself will turn out to be adapted. That means it acts non-trivially only on the past space and on our system Hilbert space. So to have a general unitary, we need to choose the coefficients as follows. We refer to these as triple S, L, and H. And for the moment, I'll just take them to be bounded operators. H is going to be the Hamiltonian. So that's going to be self-adjoint. The S is going to be the unitary. That's going to be interpreted as the operator which gives you the scattering. The L operator is effectively what does the direct coupling between your noise field, so that's the B or B star coming in, and your system. So again, we'll initiate this. This should be U at t equals 0 is equal to the identity on your system tensor, the Fock space. So we'll assume that this extends to a unitary, so on a joint space. So what you typically get is that this is strongly continuous, one parameter. It's not a semigroup, it's a cocycle. And we've heard about cocycles already this morning from Professor Arcadi. It's a cocycle specifically with respect to the time shift on the Fock space. So again, we think of the one particle space of the Fock space as L2 of R plus. So that's functions of positive time, but we can also shift these functions forward in time as well. Okay, so if we take our choice of the state as just being the Fock vacuum vector, so that's the no particle state, we get a non-continuous CP semigroup with the following generator. So this is the standard Lindblad form, or Lindblad, Gorini, Kosakowski, Sudarshan. Lindblad showed that the general non-continuous semigroup of CP maps will have combinations of these, linear combination of these as generators. If you want to recover the classical results, you'll find that the generators I looked at previously are special cases of this. It's probably not surprising. If you take the combination B plus B star, that's effectively equivalent to the Wiener process, whereas the combination lambda plus B star plus B plus T effectively gives you something equivalent in the vacuum state to the possum. Okay, so what you get from the essentially classical cases is a very special case of what we have here. And really it's the fact that we have the L and the L star together. Maybe just to emphasize this point a little bit, we can look at a damped cavity mode. So this is just a harmonic oscillator. I will take A to be the annihilator, and of course we have the canonical commutation relations, A star, the commutator equals 1. So what we could do is take the scattering element to be equal to just the identity. So there's effectively no scattering in this. So the lambda process doesn't appear. We'll take a coupling operator just to be root gamma times A, and we'll take a Hamiltonian to be just a simple harmonic oscillator with frequency omega. So if we want to look at how the mode varies over time, how it evolves over time, we again just apply the unitary conjugation here. And for this particular model, what you get for the Heisenberg dynamics for the operator A as a function of t is a sort of Ornstein-Uhlenbeck equation. What you have is a complex damping, but you also have a fluctuating part, and that's the, you can think of this as the noise field, really the annihilator noise. If you integrate this and set it equal to just the oscillator itself, A at time t equals 0, you'll actually find that A of t and A of t star have a commutator equal to 1. So it is properly unitary, and we are conserving the commutation relations at time t. Of course, if we average things out, we do pick up complex damping. Okay, so that's a very simple damped cavity mode. You couldn't really get this if everything was essentially classical. You really do need this full theory of Hudson and Parto-Serrati to get the most general case. Right. So going back to the talk by Hendra Norden a few days ago, he was talking about classical, well, he was talking about linear systems. So I'm just going to describe the general theory of singular perturbations, because this is a general class of problems I want to address here, but I just want to show you what happens in the classical world where you keep things linear. So you might have a system and its state variable, you can break into two components. One is the slow set of variables and the other is the fast set. We're going to assume dynamics for the state variable, which is linear, driven by inputs u, again in a linear way, and maybe leading to an output y, which is a linear combination of your state and the input. So it's an A, B, C, D construction. A, B, C, and D's here are all going to be generally matrices. There's an epsilon included here with the fast component. The idea is that epsilon is going to 0. So if you rearranged it, 1 over epsilon is becoming infinite. What's happening is that with the fast degrees of freedom here, they're effectively evolving very fast, but they're decaying to an equilibrium state, so that in the epsilon goes to 0 limit, they've already relaxed down to the equilibrium state. And again, this is a very old and well-established theory. To cut a long story short, what you could formally do is just set the left-hand side equals 0, put epsilon equals to 0. If we have that the coefficient AFF is an invertible matrix, what you can do is you can write the fast value for the fast variable as what's known as a slaved value to the current value of the slow variable and also the current value of the input u. And you can insert this slaved value for the fast variable into the equations, and you get a reduced system. Okay, so this is all very old stuff. You'll notice that when this works, we've got some fractional linear transformations going on with the coefficients. Indeed, these are Shor complements. Now, we're going to try and do a singular perturbation of this type here on the cavity mode. So this is a problem which I looked at a long time ago with Ramon van Handel. Our system is actually going to be comprised of two different systems. There's an atom, which in the picture is the red dot, and that's going to be contained inside a cavity mode. So that's going to be the AA dagger. The cavity mode is going to be open. It's going to be coupled to its environment, and we're going to assume it's going to be strongly coupled as well. So the idea is that we take a singular limit where the coupling of the cavity mode to the external field is so strong, effectively the cavity mode becomes enslaved and we can eliminate it altogether. And in the singular limit, we just think of the incoming field, so the environment talking directly to the atom. So the whole idea is that if your cavity mode is so strongly coupled to its environment, it effectively spends all its time damped into the ground state. Now, the type of arguments we saw in the physics literature were extremely unconvincing. What they would say is that we have gamma going to infinity, right? So this basically means that we do the same trick as in the last transparency. We've just put the rate of change for the cavity mode equals 0 and rearrange algebraically. You then get a slave value for the cavity mode and you substitute this in. And for some reason they knew, well, you substitute in normal order, Wick order, to get the right answer. So you can actually play around with this, but clearly there are some issues here. For one thing, we're taking quantum stochastic differential and we're somehow setting it equal to 0. And you'll also notice in the final answer, this gamma, which should have been going to infinity, is still appearing there. There are also a number of other issues. When they got the final answer, turned out to be the correct answer if you do it rigorously, but they argued that, well, this is somehow Stratinovich rather than Ito, and we want Ito, so they did it for the unnecessary transformation beyond that. So in our paper, what we did was to choose the SL and H coefficients, so the coefficients of the quantum stochastic differential equation, to be as follows. So n is going to be the large parameter here. So gamma basically scales as n squared. With the coupling of the atom to the cavity, we have the following type of Hamiltonian, which is effectively up to quadratic in A and A dagger. There's a number term A dagger, which has an n squared contribution. There's also an A and an A dagger term separately. The E's here generally are taken to be operators on your atom, okay? So they're not scalars, they're operators. So now we've got a quantum stochastic differential equation where some of the coefficients are allowed to become infinite. That's going to be our scaling limit. So what we were able to show, and we did this by using some results on quantum stochastic limits, where we had to do a Dyson series expansion. So we had to assume enough so that the Dyson series would converge. We were able to show that you did get the convergence of the process and indeed the Heisenberg evolution to a reduced model where the cavity has basically been eliminated, effectively we're down into the ground state of the cavity all the time, but we still have an interaction between the atom and the environment. And the reduced SL and H coefficients here are as follows. Okay. So that was in 2007. We had to use the Dyson series expansion, which was quite restrictive. We also considered the intermediate system to be eliminated as a cavity mode. And it sort of suggested that this only applied to something with a little bit of linearity in it, because the cavity mode is just a linear system on its own. That's a little bit misleading. It turned out that subsequent to this, Luke Boughton, another colleague of ours, extended this sort of result, bypassing completely the Dyson series expansion, instead using the Trotter-Kato type theorem. So that's what I really want to talk to you about. So it's probably worth at this stage just saying what Trotter-Kato theorems look like. So we'll first of all give a Hilbert space formulation of this. The idea is you have a strongly continuous contraction semigroup, Vn of t, on some fixed Hilbert space H with generator Ln. And the idea is that we have a sequence of these, say, labeled by integer n. We then have something which we would hope is going to be the limit object. So this is going to be another strongly continuous contraction semigroup. It's going to be, generally speaking, on a closed Hilbert subspace H0, because we want to allow this situation where we've eliminated something. Some of the degrees of freedom have sort of decayed down to their equilibrium value. So we're on a smaller, we've a semigroup which is acting on a smaller Hilbert space than the original one. So this limit object has a generator L, which has a core D0. So the results are the following. If we take, say, it's basically the equivalence of the following statements. The first is a uniform convergence of the approximating semigroups to the limit semigroup. This turns out to be equivalent to being able to show graph convergence in the following sense. We take any vector in the domain, the core domain of the limit generator L. What you have to do is to try and construct a sequence of vectors, each one in the domain of the corresponding Ln, so that we have non-convergence of these phi n's to the limit phi, but also the generators converge. So it's this graph convergence of the generators. So from a mathematical physics point of view, this is quite nice. You sort of encode everything into the generator, and if you can show convergence at the level of the generators in this sense, you've got a very strong notion of convergence of the semigroups themselves. There's also a Banach space version of this. So if you wanted to describe the Heisenberg picture here, so if we've now got a strongly continuous contraction semigroup family, again, under compositions. And so we've got a sequence of these on the Banach space, and each of these with a generator Ln. and we want to consider convergence to a limit semigroup, and this may well be acting on a Banach subspace B0 rather than the full Banach space again, and we'll assume that this object has a generator L with a chord D0, then convergence of the approximating semigroups to the limit object can be shown to be equivalent to this convergence on the core domain. So it's graph convergence. Right, so we've already had one talk, I think, which referred to this paper by Kurtz. The credit for applying this to quantum stochastic models actually goes to Luke Boughton, as I've mentioned, and he did this in collaboration with Andrew Silberfarb. They later involved Ramon van Handel, my previous collaborator in this, and they applied Trotter-Kato type results, first of all, to singular perturbations, but actually to a much wider class of problems as well. So I've given an indicative list of people who have applied the Trotter-Kato type result to quantum stochastic models. It's probably not exhaustive, but fairly representative. There are probably a few known suspects there. Apologies if I've left anyone out. Now, just to describe what Luke Silberfarb and Ramon did in their papers, they were able to get some very strong results. We've heard quite a bit today about the issue of going from bounded coefficients to unbounded coefficients in QSDEs. They were able to relax considerably this constraint and deal with general unbounded operators. And to this end, they tended to work as a matter of convenience with the adjoint of the unitary, basically because it gives you a right QSDE rather than a left QSDE. So if you do that, you'll notice that all the determined braces here involving the increments, they all lie on the right of the operator V rather than on the left. And that's just a consequence of taking the adjoint, and it turns out to be quite convenient to do so. So for the usual SL and H, and for any pair of complex numbers alpha and beta, we'll just introduce the following operator, K alpha beta, which is this amalgam coming from the coefficients of the quantum stochastic differential equation. Right, so what they were able to show was a specific type of Trotter-Kato result which applied to quantum stochastic differential equations. So the reference is there. It's already quite old, this result, 2008. They were able to show, again, a uniform convergence, and the equivalent condition here was that for all phi in the core domain for these K alpha beta, you assume that they all have this core domain. So for each alpha and beta, you can get, again, an approximating sequence within the domains of the approximate K alpha beta n, so that you do get this graph convergence. Second term here, sorry, there shouldn't be any n here, obviously enough. So that's quite a useful result. You need this because you're, in addition to trying and get the approximation on just the system space, you need to deal with the general Fock space component as well. So if you can show that for arbitrary exponential vectors, you can sandwich this in between, you can get the result, and that's where the alphas and betas are coming in from. So I'll just describe, and this is largely with hindsight, what they do in the paper. It took us a bit of a while to figure out exactly what the limit is, because they stated in terms of quite a complicated set of conditions on the coefficients involving projections onto particular subspaces. A somewhat clearer way of describing this is as follows. So this is really came out of work with Hendra Noorden, where we were trying to understand what was going on in the adiabatic elimination models. Effectively, you take your Hilbert space for your system, and what you want to do is to decompose it into a slow subspace and a fast subspace. So it's a direct sum like this. So the whole idea is that the fast subspace is going to be the subspace that's eliminated here. With respect to this decomposition, we can consider describing operators on H decomposed as follows. So there's a slow part, a fast to slow, a slow to fast, and a fast to the fast subspace part. With respect to this representation, what we want is, first of all, the scattering operators basically to be fixed and independent. The coupling operators, we want these to have a part which are singular, but there are terms which are not contributing. It's just the fast to slow and the fast to fast components which are allowed to be non-zero. So that's going to be the divergent part, then plus some fixed term L0. Likewise, the Hamiltonian part, the slow to slow part is going to be fixed. The fast to slow and the slow to fast is going to have something which is order n, and the fast to fast part, that can have a contribution which is order n squared. So if you look at the following combination, -1/2 L star L minus IH.
Sorry,
independent.
there are 4 minutes left.
Yeah, I'm nearly done, don't I? This, incidentally, is the effective damping operator we saw in, I think, Professor Philippov's talk earlier. Basically, we're going to get the lead term here, the most divergent part, the n squared bit, is going to have only one quadrant, the fast to fast part, which can be non-zero. And specifically, we want this to be invertible on the fast subspace. In practice, what you actually do is you look at your coefficients of the QSDE, you construct the following effectively complex damping term. You then say, well, what we want is the kernel of this space. That's going to be this, define what the slow space is, and the complement to this is going to be the fast degrees of freedom. So we're still not done with the Bouten, Van Handel, Silberfarb paper. Again, just coming up with the criteria they use. We'll introduce the following triple of coefficients, S hat, L hat, and H hat, defined as follows. And again, you'll notice we're dealing with Schur complements again. And additionally, they want a further condition, which is the one in the green box here, the fast to slow and the slow to fast elements of the scattering are equal to 0. So this basically means no scattering in the limit between the fast and slow subspaces. And they also want the effective coupling to the fast degrees of freedom to vanish as well. So when you've got all of these conditions, they're able to prove the following result, that if you consider P of S, this is the projection onto the slow subspace, then the sequence of unitaries parameterized by this n, which is an increasing coupling strength, as n tends to infinity, we get this uniform convergence to this limit object u hat, where u hat is described by these coefficients s hat, l hat, and h hat. Okay, so this is quite a powerful technique. I thought I'd give you just a flavor of the result of the Trotter-Kato terms that are out there. The Trotter-Kato result itself is quite useful. It extends beyond problems like adiabatic elimination, and it has cropped up in quite a variety of other problems as well. I should mention one where you're going from a discrete to a continuous approximation, where the limit object will turn out to be a time-ordered exponential of Halevo type. So that they were able to come up with a discrete to continuous approximation. This also makes clear a number of results due to people like Stefan Attal and Botra, as well as describe the type of limit processes which Alexander Halevo had in his papers on the time-ordered exponentials. There's probably some connection here with the results on Chernov's theorem and some of the other talks. And one of the things I'm looking at the moment with Oleg Smolyanov, Yuri Orlov, and Professor Sakbayev is similar applications to completely positive maps. But this has actually turned out to be quite a useful technique to apply to quantum stochastic differential equations. It's a very nice result, very powerful result. Again, it needs a bit of imagination in how you apply it, but the Trotter-Kato terms, again, not my idea, I wish it was, it really goes back to Luke Boughton. Very nice idea with quite a lot of applications to quite concrete problems in quantum optics and general quantum open systems. Okay, so I'll finish with that. Thanks.
Thank you very much for your great talk. So we have several minutes for questions, please. Anybody has a question, just go ahead.
I have a comment.
Please.
From my point of view, it is very nice talk, a beautiful talk. On one hand, it contains a lot of information. On other hand, it is very stimulating. And after that, one wants to join to this direction and to start to work in this direction. So many thanks to the speaker.
Thank you for the comment. Great. So everybody is invited to give further comments, ask further questions, or to join this direction of research.
Well, actually, I had a question, but John has already answered that. So natural question, so that in classical theory of operator semigroups, one proves Chernoff theorem using Trotter-Kato. So if you have Trotter-Kato for quantum stuff, then next step would be Chernoff theorem, of course.
Yeah, be careful about Trotter-Kato. This is not the Trotter-Kato product formula, yeah?
Yes, yes, this is a Trotter-Kato theorem, yes, but it is used in the proof of Chernoff theorem in the classical situation.
That's true, yeah.
So now the next step would be to have a Chernoff quantum theorem.
Well, we have proved with Professor Oleg Galkin a version of theorem which is similar to Chernoff theorem. It does, and it is based on some very, very different things without any Trotter-Kato or some other profound results. We have a preprint of that. On that, you can look at it.
If I may have a comment.
Please.
I think that calling this theorem Trotter-Kato is a bit of overdoing, because Trotter-Kato and Neve, by the way, they have proved this version with resolvents. So the original Trotter-Kato theorem concerns equivalence of convergence of semigroups and resolvents. Now, and it took several years before Thomas Kurz and independently Miroslav Sova have proved that that convergence of semigroups is equivalent to this graph convergence of generators. So I would rather call it Sova-Kurz theorem and not Trotter-Kato theorem.
Okay, I'll bear that in mind. I should actually say that when we looked originally at the Boughton-Silberfarb paper and tried to figure out what they were doing, in particular, try and understand the vast array of conditions they had to make their theorem work, in order to actually get some insight in this, we went instead to calculate the resolvent for this operator.